Okay, please. Then please use this microphone.
Right. All right. Oh, that's wrong. So thanks a lot for the invitation. It's my pleasure to be here. As we were discussing, I've been here a long time ago when I was a student. It's great to come back. So, all right. So today I'm going to discuss something that we recently did with bunch. Oh, how to move this? Oh, here. Okay. Yeah. Okay, well, actually, before starting, big thanks to the organizer, to Shin, Hidetoshi, and Masaru. Very happy to be here. So my talk is based on these two works that we did in collaboration with a bunch of great people, and in particular, big thanks to the young one that did good work. You can find here the details, and I will not refer too much to them in the rest of the talk, but you feel free to ask me for reference after if you didn't take note here. So the main question that I want to address today, it's somehow related to the basics of the applied holographic prescriptions, and in general to the holographic dictionary itself. So the idea that you find many times repeated in talks and in papers is that holography is a duality between some gravitational bulk descriptions and a dual boundary QFT where there's no gravity. And at least in this form, this statement is quite unprecise. And the reason why is that if I give you a specific gravitational bulk action, this itself does not uniquely defines a boundary quantum field theory. And in particular, there is an additional ingredient, which is extremely important, together with the gravitational bulk action, which is the boundary condition for the fields that live in this bulk spacetime. So we have this bulk spacetime that for me here is indicated like a D+1, let's say, spacetime, where of course we have gravity. So there is some kind of Einstein-Hilbert or generalization of it there. And there are a bunch of matter fields, which, for example, in my case, will be the gauge field, which will have its Maxwell, let's say, kinetic term in the bulk. And every bulk field will be determined in the bulk. So the profile of these bulk fields will be determined upon describing the boundary condition at the boundary of ADS. So my spacetime by construction is an anti-de Sitter spacetime. It has a boundary, and I have to implement a boundary condition there. The behavior of the fields there is usually a power law, as you can see here, and I have to specify what I'm gonna fix at the boundary, and only when I do that, then I completely and uniquely specified what is the boundary QFT that I'm interested in. So let me start with a concrete example, which it's quite simple, so we can all understand what I'm saying. So here I'm considering a four-dimensional spacetime, and my bulk theory is just, can you see the cursor? I'm not sure. So my bulk theory is just Einstein-Hilbert with a negative cosmological constant plus a Maxwell term. So this is a simple bulk action, which is called Einstein-Maxwell action. And it has a simple solution, which is given by this metric here, which is just a black hole metric with a blackening factor f of r. R will be my extra dimension in the bulk. And then I will have a gauge field, which contains both a time component and a space component. And these in general will take care of charge and magnetic fields in the boundary description. And then what I'm doing is that this bulk gauge field, which is in general a function of the holographic coordinate and the boundary coordinate T and X, has a profile close to the boundary. So for my coordinate, the choice of the coordinate that I made, this boundary is at r equal infinity. And then I have two different power, let's say, terms, which are completely independent, which are the two independent solutions of my differential equation at the boundary, if you like. And the the usual, let's say, dictionary is implemented assuming what is called standard quantization, which is nothing else than Dirichlet boundary condition for this field. So what we do all the time, or well, most of the time at least, is to fix this zero term here. So what we call the leading term. And this in the boundary will correspond to a source for a dual operator, which I call J mu, and at the bottom of the slides. And this operator, or better, its vacuum expectation value, is given by the subleading of this expansion, which is uniquely determined once I specify the leading term. So in other words, if I start from the bulk action on the top, and I add the boundary condition that you see here in the middle, fixing A0, I ended up to a boundary field theory description. Now the Z is the generating functional of the boundary CFT. There's no gravity here. And this is nothing else than a quantum field theory, if you like, sometimes like a CFT, where you have an operator, which is a vector operator, which is a current, which is conserved because of the gauge invariance in the bulk, is this J mu of phi. This is a composite operator. So is an operator of the fields phi, which is a collective label for all the kind of microscopic fields that you have in your field theory. And A mu is just a source for it. So you can see I'm deforming my S0, so let's say the CFT action, with a deformation, which is just the direct coupling between this source and this conserved current. So this is what one can do. And if one does what I just outlined, you can ask yourself, so what is the boundary description? What I'm really describing here. And what you're really describing is a quantum field theory where there is a conserved U1 current and in presence of an external gauge field. So if you're interested, if you like, at the low energy, let's say, physics of these systems, then the low energy physics is described from these two hydrodynamic equations. The first one is nothing else than the conservation of the stress tensor up to sources. And the second one is the conservation of the U1 current. Both of them come from symmetries. And then you can start asking yourself what the physics of this equation is going to give me. And for example, if you consider the gauge sectors, you will find that there is a mode which is diffusive. And this mode is nothing else than the diffusion of this conserved charge associated to this current J mu. And it's nothing else that, for example, when you throw some colors in water, that's just diffusion. Now, the question that one can ask himself is this everything we can do? And in particular, if you think about applications, these prescriptions can be quite unsatisfactory in many physical situations, especially for condensed matter system, but not only. So there are many situations in nature where, of course, the gauge field plays an important role. The dynamical gauge field plays an important role, not as an external source. And where Coulomb interactions, which are, of course, driven by this gauge field, are important. Of course, the typical case is electromagnetism, which is a theory based on dynamical gauge fields. Plasmas are, realizations of electromagnetism, if you like. And then there are many condensed matter situations where dynamical gauge field is important. And one of them is plasmon physics, which is responsible for these very nice colored glasses that you see in medieval churches. And the second one is superconductor, where you see, for example, the levitation effect due to Meissner, which is very beautiful and is again given by the fact that there is a gauge field there, which is really dynamical. So the first part of this talk, I want to show you that indeed it is possible to implement this kind of situations from holography. And the way to do that, which of course I didn't discover it, is to use a different boundary condition for this gauge field. And what I want to study today is basically how much of the boundary description I can recover using this mixed boundary condition or this more generalized boundary condition. And in particular, I would like to do two things today. So the first thing that I would like to do is I would like to rediscover Maxwell equation in the boundary, and I would like to generalize them to what is called magnetohydrodynamics, which is basically the hydrodynamic theory of systems with dynamical gauge field, if you like. So with dynamical electric and magnetic fields. And after that, I would like to show you how to build a real holographic superconductors and how to recover standard physics of superconductors, like the Higgs mechanism, for example. Also, one thing that I repeat, if anybody has questions both here or in the Zoom, please interrupt me anytime. I prepare a lot of things, but I want this to be quite informal. So let me start from the reason why we started, or at least I started thinking about this problem. So in the recent year, there's been a lot of effort in describing or in let's say rewriting Maxwell equations using new mathematical structure, which are called higher form symmetries. And the reason why is the following. If you think about Maxwell equations, or in general electromagnetism is usually written down based on a gauge symmetry. And gauge symmetry is not really a symmetry. It's just a redundancy of a theory. So it's quite, let's say, it's not that nice to use a gauge symmetry to actually write down an hydrodynamic theory, whereas hydrodynamics is usually a theory built on conservation law, so on global symmetries. And therefore, these people try to argue that electromagnetism itself can be understood without invoking ever a gauge symmetry, but just talking about global symmetries. And I don't want to enter too much into the details because that's not the topic of my talk, but the reality and the result of this program is that one can completely forget about the gauge symmetry of, let's say, electromagnetism, and can write down the hydrodynamics, or if you want, the magnetohydrodynamics for these systems, just considering the stress tensor, which of course is there, and the new new global symmetries, which is a higher form symmetry, which is written in terms of this two-form current, which, as you see in this equation 1.2, is nothing else than, if you want, the dual of the standard electromagnetic field strength. Okay. And so what happened is that this equation, the Bianchi identity, which is in the Maxwell equation, which is not a dynamical equation in the standard formalism, becomes here the main equation of the story. Now, why I wanted to discuss this, because then people started to ask themselves, what happened if now I consider these different theories in the bulk? So these different theories, as you can see, as basically the Einstein and Maxwell term, sorry, the Einstein-Hilbert term. So you can see the Ricci scalar, you can see the negative cosmological constant, and then you see that instead of putting the Maxwell term, here they put a generalized Maxwell term for an object with one additional index. Now, if you think about which is the field strength of a two-form, now if you think about this action, you immediately recognize that there is a gauge symmetry, which is these two forms shift by this d lambda, where lambda here is a one form. And then just by using the holographic dictionary, you will see that there should be a conserved two-form current at the boundary. And therefore, in principle, if I write down this theory, I should recover exactly what this theory is telling me. So then there is a puzzle. What is the puzzle here? The puzzle is that if I follow this prescription, the boundary description of this theory should be basically electromagnetism. But now think about the bulk. If I think about the bulk, the only thing that I'm doing is a Hodge dual. I'm just Hodge dualizing the field strength in the bulk. So then how a Hodge dual in the bulk can change the physics? And the answer is that the bulk picture is not changed at all. So the bulk physics is exactly the same, but the boundary physics is completely different because this Hodge dual in the bulk is not preserving the boundary condition. So in reality, and that's basically what I want to discuss today, is what this theory here is hiddenly doing is modifying the boundary condition. And so, as I said, what do they get? What do they get when they study this theory in the bulk? They get what is called relativistic magnetohydrodynamics. This is basically a quantum field theory with a dynamical gauge field. So there is a dynamical electric field, a dynamical magnetic fields, and there are a bunch of new phenomena which are observed in nuclear matter and plasma physics, like these Alphen waves or magnetosonic waves. So these are new excitation that comes because you have additional degrees of freedom, and you have Maxwell equation coupled to matter that start having, you know, making funny games. And these people were able to recover all this physics starting from the holographic picture. And of course, there are some advantages, which I will not answer right now, but of course, hydrodynamic and magnetohydrodynamics is a well-defined, let's say, setup, but unfortunately, hydrodynamic is more subtle than what we believe. And holography, on the other side, once we write down the correct action, everything follows. So we can get completely all the constitutive equations. We don't have any problem of expanding a small b, large b, small gradient. We can have the full story. And then it's much easier to check or compare if anything was missed or not in the hydrodynamics. And this happened many times, for example, in different contests, that holography helps hydrodynamics to discover pieces that were missed in some of the construction before. Of course. Wait a second, I think. Yeah.
Yes. So on the one hand, you want to introduce the dynamical gauge field by doing the mixed one. Okay, I know the story. So you want to introduce the dynamical gauge field. How do you treat the QFT part or conformal field theory part? Do you also want to include the full dynamics, or usually you just introduce some conformal operator in the large n limit and calculate coordination function or those kind of things that you can calculate without knowing any dynamics of the conformal field theory? How do they interact?
So if you wait a few slides, I think I have a field theory slide that answered that question.
Okay, thank you.
So just, if it's not clear after that, ask again. So back to what I want to do here. So the first thing that I want to do is I want to discover what's the trick behind this higher form bulk description. And the second thing that I want to ask is if we really need all this fanciness. Do we really need this higher form bulk description or not? And is there another solution? And the story, at least the first part of the story today, is that in order to discuss magnetohydrodynamics and therefore a quantum field theory with dynamical electric field and magnetic fields in the holographic picture, you actually don't need higher form symmetries. You can use them if you like them, but that's not necessary. And indeed, there is a very beautiful map between standard gauge field and higher form symmetry that I will just show you in a while. Back to the field theory. So let's start with the standard picture in holography. So if I follow the standard dictionary and I impose the Dirichlet boundary condition, then all my fields are just external sources. There's no dynamics for the metric, for example, or for the gauge field. And therefore, what I'm really doing at the boundary, I have the generating functional of my CFT, which is basically expressed in this form. And I'm deforming the CFT, if you want, action in terms of these minimal deformations, which are just expressed in terms of source and VAV of the operators. So I have these A mu and J mu, which I'm not integrating on. So these are not dynamical fields. These are just static external sources coupled to the corresponding currents, which are conserved. These currents, again, are composite operators of this phi, which represent the degrees of freedom of my CFT, whatever it is, or my quantum field theory. And then what I'm doing, I just do the standard, field theory. If you want prescription, I just take functional derivative with respect to sources, and I can compute all the 2-point function, 3-point function, 4-point function, depending how strong I am. Okay, so from here, just using standard field theory and of course the holographic dictionary that allows me to map the things, I'm able to get the 1-point function, 2-point function, and all mixed things. This is the standard story. Now, if I want to make, if I want to have an action in which my gauge field now becomes dynamical, what I have to do is two things. So the first thing that I have to do is I have to do a Legendre transform, which is basically which shift the degrees of freedom of my theory from the current that before was my dynamical degrees of freedom to the gauge field. So now the current becomes an external current, and the gauge field becomes actually my degrees of freedom. This is the Legendre transform. And then I have also to add a kinetic term for this gauge field, which is the Maxwell kinetic term. So then what I do, if I now take a variation with respect to the gauge field of this action in the field theory, what I get basically Maxwell equation. Okay, so this is what you find down there. These are just a standard Maxwell equation where there is some matter part of the current that this, imagine you have some scalar or something else. This is the matter part of the current, so all the charge operator will enter there. And then there is an external current, G mu external, which now is really an external current. So it's my source that I'm applying from outside. Okay, so this is basically my goal. And of course, here you see, I imposed by myself the Maxwell equation. If you like, I added the kinetic term to be Maxwell. In principle, you don't need, but for the moment, that's the easiest thing that you want to get. You want to get Maxwell equation. In principle, if you want to get something which is more complicated, more nonlinear, then of course you have to add some more nonlinear kinetic term or higher order kinetic terms, but this is the minimal things that one would like to do, okay? So, and then, okay, then if you start from here and you just try to understand what is basically the equation of motion that determines the dynamics of these systems, well, the equation of motion are exactly what you expect. So you will have the conservation of the stress tensor that now can be decomposed into the stress tensor of the matter and the stress tensor coming from electromagnetism. The stress tensor of electromagnetism is, of course, a standard stress tensor that you get just in, standard electromagnetic theory in terms of the field strength. Then you get the Maxwell equations, which are just the equation below. So the dynamical part of the Maxwell equation, if we want to be precise. Then we get, of course, also the associated Bianchi identities, which is just an identity that comes out from basically the definition of the field strength, if you like. And we get the conservation of the matter current. So you can see this conservation of the matter current. In reality, all the equations that I wrote here, most of them are redundant. So you can see, for example, the conservation of the matter current on the top. If you just take a divergence of the left side of the equations, that follows automatically. So it's not really needed. But I wrote there just to, for completeness. So this is basically the field theory point of view. And what we want to do is, so we know well how to do this from holography. This is what we do all the time. This is a bit less known, even though many people work on this. And that's what we want to do. Now, what is the idea? The idea, which again, it's pretty old. Indeed, it was basically discussed almost after the description, the discovery of holography. It's, to my knowledge, the first discussing this kind of boundary condition was Witten. And in the context of gauge field, I think that the most important paper is a paper by Maroff and Ross. And the idea is kind of simple. And is a generalization, of, if you want, of what one can do for the scalar. So if you take the gauge field, as I said, and let's take in ADS, then the boundary asymptotic for this gauge field has two terms. And in principle, the most generic boundary condition that one can impose at this boundary is a combination of these two terms with some certain coefficient. So this is this alpha A0 plus beta A1. So these are usually known as mixed boundary conditions, and they reduce to what, let's say, is done in the standard quantization if you set beta equal to 0. So if you set beta equal to 0, you go back to the old story, and you find out that basically what you get is this CFT plus deformation, where the gauge field is external. So if you set beta equal to 0, the gauge field is external. Now, let me just point out a bit of history, just for those of you who are not familiar with that. So the first application, at least that I know, of this mixed boundary condition in terms of applied physics is in the context of holographic superconductors. So probably many of you or all of you know the holographic superconductor model. This is a very famous model in the applied holographic business, which was introduced in 2008 by Arnold Herzog Horowitz. It's usually indicated like HHA model. And I mean, this model is great, but the title is horrible. And the reason why the title is horrible is this model is not a superconductor. So this model actually represents a superfluid. And many authors immediately, realize this issue. And at least to my knowledge, one of the first papers that really used the real holographic superconductor model is this paper from 2009, where people started studying the vortices in these holographic superconductors, and they realized that they really needed different boundary conditions to realize the physics of superconductivity. And I will say more about this because the second part of the talk will be about that. Now, recent applications also, which is pretty nice, is the realization of plasmons in holography. This is another nice piece of work that, of course, so plasmon are excitation, longitudinal excitation of charge and electric field, which can be, are discussed in electromagnetism in any textbook or courses. And they just come out from basically Maxwell equation plus the assumption of the Drude model for the conductivity. And so these plasmon are nothing else than the fact that the light in the electric or in a material with matter gets a mass, and this is known as plasmon mass. And of course, this has a lot of important properties for what we see all the time, all the day, like why metals are shiny or why these nice glasses are colored, and all the properties between light and matter. And this was recently realized in holography, again, using modified boundary condition because of the need of getting Maxwell equations. And this is also a very nice paper, recent paper, where, again, these mixed boundary conditions were emphasized to clarify that in order to get the real physics of superconductivity, which in this sense is Meissner effect, the reason why basically this magnet is levitating, you need to have this mixed boundary condition. And so back to the higher form trick, while I was trying to understand why these higher form fields work so well in holography, I discovered this paper, which is, again, a very nice paper. I really suggest the reading. So here, they basically solved my question. So they show the following. They show that even if, so let's assume you start from a Einstein-Maxwell bulk theory, then we know that with the Dirichlet boundary condition, you will get basically an external gauge field in the boundary. And with alternate boundary condition, here they call it alternate, you will get dynamical U1. Now, in order to get the higher form in the bulk, what I have to do, I have to do a notch dual in the bulk, which in this figure here is called electromagnetic duality, because that's what it is in electromagnetism. So you do this electromagnetic duality, and then you see the gravity side is not described anymore by a gauge field A, but it's described by what they call a magnetic gauge field B, which actually, well, depend on the dimension, but it's not a gauge field. It's actually an higher form. It's usually, for example, in ADS4, this would be a 2 form. And sorry, in ADS5, this would be a 2 form. And then what you see here is that now you see for this higher form, the regular boundary conditions are actually the one which implement dynamical electromagnetism. And the alternate boundary conditions are the one that implement the external source, the global U1 symmetry in the boundary. So what is happening here? Why this higher form really worked easily without doing anything funny? Because evenly this higher form, this electromagnetic duality in the bulk, is switching your boundary condition at the boundary. So you can convince yourself that this is the case just thinking about the electromagnetic duality. Electromagnetic duality, you are multiplying basically the gauge field by an epsilon, which has a bunch of indices up and down and the square root of G. So this will change completely, will switch completely the asymptotics, because there will be a factor of R jumping around. Anyway, so the answer to my questions is that these higher form are a very fancy way to implement mixed boundary condition. So all you are doing, you are basically doing mixed boundary condition. And then what we ask is like, okay, is this really true? Is this really happening? And so am I able to basically recover all magnetohydrodynamics just using standard gauge field in holography without thinking about any higher form symmetries or anything like that?
So,
and then what we did is, of course, we seated on the shoulders of the giants, and we basically performed this exercise. So again, my boundary conditions, the boundary condition that I want to impose are these boundary conditions that are written on the top, which are, again, Maxwell equations, where this pi mu is actually what usually we call the J mu, and is the current which is obtained from the variational principle on the shell action, the matter part. And in the holographic perspective, this is given by basically one component of the field strength in the bulk. And then, well, these are just, once you do this prescription and you apply it to the fields, you get some, nasty equations between the external current and the asymptotics of the fields. Let me just explain very briefly what they are. So everything that you see here with L means leading, and everything you see with S means subleading. So you see that now the boundary condition that we're putting are really a combination of leading and subleading. And the moment, there is one parameter here which is very important, which is lambda. So lambda, as you can see on the top left, is the gauge coupling, or is proportional to the gauge coupling. So this is nothing else than the strength of Maxwell interactions. And you can see that if I send lambda to 0, what I get is basically that the subleading disappear and I go back to standard boundary condition. One thing that I didn't emphasize well is that the boundary condition that I'm really going to put are, I'm going to put external sources to 0, which means that now these external currents must be set to 0. So basically my boundary condition are this equals 0 and this equals 0. This would be my boundary condition. Notice that there are factors of omega and k jumping. This will play a role. I will explain later what kind of role they will play. Yeah. Yes.
So do you assume 4D bulk and 3D boundary gauge field?
Yes.
So that means that so lambda has the dimension. So what happens if you say take lambda to 0? Do you have some non-dynamical gauge field?
I will show you.
Okay.
So actually, well, let me say it briefly and then I will show you. So what happens if you set lambda equal to 0, you are basically killing the interaction between the photon and the matter. So you will see a decoupled photon staying there, but it's not a photon of the CFT. It's completely decoupled. It's just there.
And also, so in these equations, do all gauge field boundary field, or I mean, I'm a bit confused. So are these bulk gauge fields or boundary gauge fields?
Yeah, this slides is maybe so L and S are basically the subleading and leading term of the expansion of the bulk field. So this is all a boundary statement.
Okay, this is all the boundary statement. So in the equation above, so F and S on shell, are these bulk quantities?
Yeah.
Okay. Okay, so thank you.
Yeah, I haven't been very precise. This is the standard. This on the top is the standard top right is the standard prescription to find the current at the boundary in terms of the bulk. And below, everything is in the boundary. So L is always the leading coefficient in the expansion of whatever fields you are looking at. And S is the subleading.
Thank you.
Excuse me. Can
Yes.
you hear me?
Yes.
So may I ask a naive question in the previous slide?
Yeah.
Before this slide, sorry. So here you have some kind of the correspondence, and I'm a little bit confused that so in the left side we have the electric theory or the taking the electromagnetic theory. You may describe the same theory using the dual gauge field, and I think this is equivalent theory in the sense that if we can compute some correlation function for the corresponding operator, they show the same result, I think.
Yeah, so let me maybe explain a bit better. So on the gravity side, if you do this electromagnetic duality, you are totally right that the gravity theory is exactly the same. You are not doing absolutely anything. But then what you are basically changing is, so as I said at the beginning, the gravity theory itself, so the gravity bulk dynamics does not uniquely fix the field theory dynamics, the boundary. In order to do that, on top of the dynamics, you have to tell me the boundary condition. And the claim here is that indeed the bulk dynamics will remain exactly the same as you say, it's just in terms of a gauge of dual field, but the boundary condition will be switched. So if you consider, let's say, the standard electric gauge field or its dual, the bulk description is exactly the same, but the field theory, which is dual to that, is not the same.
So you mean that field theory, global U1 symmetry theory, and the local gauge theory is different, but you can control the difference by choosing the appropriate boundary condition for the bulk gravity theory. Is that your statement?
Yes. So you can control it. There are two ways. You can change the boundary condition for the standard gauge field, or instead of doing that, you can do a notch dual of the bulk gauge field, and that automatically change for you the boundary condition in the same way. And there is a precise mapping, which is exactly what this paper basically work out.
Okay, thank you very much.
No problem. Yes.
So now you are trying to introduce the dynamical U1 gauge field.
Yeah.
And so, you know, the U1, if we have only U1 gauge field alone, then they don't interact, right? But once we put everything in the language of gravity, it interacts with everything. So if this is, in that case, so do you have any, what? So in your theory, you have dynamical U1 gauge field as well as some charge or something that makes the U1 photons can interact with each other.
So
yeah.
that's a good question. So the problem is not really when you put gravity in. The problem is when you couple matter to it.
Oh, okay.
So that's also why, I mean, I find our prescription easier because I always think about gauge field in the bulk, so I have more control on the coupling. Now, if I do this Hodge dual, of course, also the coupling to matter are kind of switched. Instead of coupling to matter, you have to couple to vortices or things like that. And it's not obvious to me how to do it. So the people that did this higher form trick for the moment, they just consider pure higher form. So it's not obvious to me how to couple matter to it, like standard matter. So for example, if you want to couple, let's say, a charge, like, for example, let's think about a charge scalar, right? So if you have a charge scalar in the bulk, you know how to couple it, let's say, minimally to a gauge field. That's very simple. Now, you see immediately that if you want to do the Hodge dual of that thing, you run into trouble because the coupling is A mu, D mu phi. And now you want to Hodge dualize A mu. And that's a problem. So you cannot just do it like this. You will get something non-local. So I'm not sure what's the answer to this question, but I think this should be very similar to basically consider vortex-particle duality or these kind of things. I have no idea in the boundary how this is reflected. That's a good question. I don't know.
Yes, but somehow we should introduce something that makes the photon interacts with each other. Maybe, no?
Yeah.
So is it, my question is that, is it necessary to make this formalism consistent?
Well, I mean, you can have matter or you cannot, you have no matter. That's up to you. In principle, there is a current, part of the current, which is the matter current, which at least in my language can be easily implemented. In the language of design from symmetry, it's not obvious to me how to implement this current because that current would be so basically, the fundamental particle now will be associated to the magnetic degrees of freedom. So I think in that language would be easy to put like magnetic charges, like monopoles or things like that. It's not obvious to me how to put electric charges. They would probably be something like more non-local, like some loops or some Wilson loop or something like more. I didn't think about it, but the question is, I don't know how to do it, and it should be done. And these people didn't do it, so I don't know.
So my understanding is that anyway, if we make a Hodge duality in the gravity side, somehow we are introducing some matter or charge or whatever.
No. We are just describing the same gauge theory in a dual formal, in the dual form. It's like, think about particle vortex duality if you want, or just the dual. Then you can add matter, of course, but if you add matter, then you have to take care of couplings, how to couple the matter, etc., etc. But in principle, you don't need to put matter.
Okay, so suppose that we don't have any matter,
yes,
charged matter in the theory, then is your U1 gauge theory still free theory?
Okay, so now we're going to another topic, which is how that basically what fixed points, relevance, irrelevance, or where you flow.
So my confusion is that U1 gauge theory should be free theory, but in the gravity side, things should interact with everything. So it sounds that the dynamical field cannot be free. This is my confusion.
So when you say free theory, you are thinking about the boundary or the bulk?
Oh, okay, so for the boundary, we have U1 gauge field theory. And yeah.
Okay.
Then it's a completely free theory in the language.
Then it's exactly what it was asking. Is the lambda equals 0 limit, basically. You are basically decoupling matter. So you can see from the Maxwell equation. Oops, why cannot move?
Yeah, okay, yeah.
Yeah. So you can, look, for example, okay, this is maybe not the best equation, but look at the equation on top. Multiply everything by lambda. If you then take the lambda equals 0 limit, you're basically decoupling matter.
Okay. Yes.
So lambda is the guy that tells you how much this photon interacts with matter.
Yeah. So let's consider the case of lambda equals to 0.
Yes.
Yes. Then we have only Maxwell field.
You will see
in the
a pure photon.
Yeah, pure photon.
You will see.
Yeah. But if we convert the things into the language of gravity,
Yes.
then gravity interacts with themselves. No?
Yeah.
So
It's not one-to-one correspondence. It's not
Okay.
just gravity boundary. You need
So
to.
if we compute some interaction in the language of gravity, it is still free. This is what you are saying.
I'm not sure I understand.
Okay,
I mean, there is one thing that the Maxwell theory that you have in the bulk has nothing to do with the Maxwell theory that you have in the boundary.
of course. Yeah,
And
I know.
this depends a lot on the boundary condition. So actually, if you put, for example, the standard Dirichlet boundary condition, there's no Maxwell at the boundary at all. But there is Maxwell in the bulk. There's no problem with that.
Yeah.
So the dynamics in the bulk is the standard, you have a Maxwell gauge field in a curved spacetime. And that will always be the same. I'm not changing that. What I'm changing is the boundary description where there's no gravity. And that is done through the boundary condition.
Yeah, so perhaps I can ask in this way. Okay. So suppose that you have dual field and in the gravity side.
Okay, so you want to do a notch dual to the Maxwell field in the bulk.
Okay, so there is some degree of freedom that corresponds to the degree of freedom of Maxwell field in the boundary.
Okay.
So you have some field in the gravity side.
Okay.
And that field should interact with the graviton in the gravity dual.
Yes.
And that graviton should represent something about the n equals to 4 super meter.
Yes.
So this means that U1 field interacts with n equals to 4 super meters.
Well, for example, let me go back to the hydrodynamics. You see, the electromagnetism and stress tensor are coupled now. So they talk to each other. So if you want that part, the graviton takes care of the stress tensor dynamics. Now you have Maxwell equation on top, and of course, they talk to each other. They are not decoupled. So this is the full picture. So the graviton will still corresponds to the stress tensor, and there the boundary condition, the holographic dictionary, whatever will be. Well, actually, it's not the standard because you see there is also part of the stress tensor which is electromagnetism, because you have to remember that the stress tensor is defined as the variation of the boundary metric. So you will pick terms also from the Maxwell boundary term, which is exactly the electromagnetic stress tensor. So that's basically the interaction between gravity and Maxwell.
Yeah,
basically.
I think we can.
I can maybe I can write something on the blackboard. It's easier.
Yeah, we can discuss later.
Yeah.
Excuse me, can I make a comment?
Yeah, of course.
This is Makoto.
Hey.
Hi. So let's see. Regarding Nakamura-san's question, what he's well on the boundary side, you can say he's talking about n equal 4 super mils with U1. So his U1 is not a free theory.
Okay. Yeah, I agree. Thank you. There was another question?
Could you go back to the main slide, could you go to the slide where you explained about the boundary condition on the gauge field? I think with L and S. Yeah, that's the one. And so you are going to impose the mixed boundary condition on the bulk gauge field. And is the leading part with subscript L correspond to the non-normalizable mode in the bulk?
Yeah.
Yeah.
So in order to do that, I didn't enter much into the details. This is very clear in the case of the scalar. You can do this without having troubles only if both are normalizable. And in this case, so for the gauge field, for example, in ADS4, that's for free. If you go to ADS5, you will see that you will have issues. because one of them will not be normalizable. And then the solution is that, one of the solutions is that you have to put a UV cutoff. Then if you put a UV cutoff, you have to think, what is that? And at least in the Maxwell theory, there is a nice interpretation, which is basically the Landau pole of Maxwell in 4 dimension. And yeah. So you have to be careful. Yeah, I didn't spell out all the details. This is just pictorials. But in our case, we stay safe. So we stay in ADS4, where this is basically, because the coupling is marginal, basically everything follows very easily. But of course, you need to be careful, because otherwise, if the coupling becomes irrelevant in the UV, then you will explode. And then either you put a cutoff or you have troubles. And indeed, you can put the cutoff. For example, in Makoto paper, you can see the details with the Maxwell boundary condition. And in this paper, here, you will also see that if you do the same game here, you also need to put this cutoff, because you will see that otherwise the boundary conditions are not okay. Yeah. So yeah, there are many details that I'm not specifying too much.
So in your talk, you are basically focusing on the 3-dimensional dynamical Maxwell field on the
Yes, because it's the easiest. Unfortunately, you miss a bunch of physics, and of course, our world is not 3-dimensional. But it's the starting point to what we wanted to show is that this works, and you get completely the full structure of magnetohydrodynamics. And then, in principle, you can go to more interesting questions or setup.
Is there any essential difference between the 3-dimensional and 4-dimensional?
Yeah, there are. Well, one of is exactly the one you asked. That one renormalizability. In the UV, the behavior in the UV is totally different. The second one is that if you are interested in magnetohydrodynamics, if you consider 3-dimensional, then the magnetic field is not a vector; it's a pseudoscalar, and therefore you are missing a lot of physics, because all these Alphen waves and magnetosonic waves that I was telling at the beginning most of the physics, which is interesting, come from the fact that you can have an angle between the magnetic fields and the wave vector. In 3 dimension, basically, you cannot have that. So a lot of these excitations are actually killed. And to see them, you need to do the same exercise that we did in ADS5. In principle, again, the only complication is that things become more complicated, but there's no technical or fundamental difficulties. It's just that more equation, the asymptotics are more complicated. You need to put a cutoff, and you have an angle. But it's exactly the same type of computation. I don't see any difficulty there.
Thank you very much.
No problem. What I was here. Oh yeah, going back to what I was saying. So yeah, the first thing which I want to mention, because it's something, it's something funny, because I didn't know about it. And so when we were computing this. The thermodynamics of our dual field theory, we were doing like the standard prescription, and then we find out one thing which I knew about it, and which is that the fact that when you have magnetic fields, the pressure, the hydrodynamic pressure, is not anymore the mechanical pressure. This is a well-known fact, and indeed you recover it here. For those of you who are familiar, for example, with other type of model in holography, like the axial model, this is the same thing that happened there. But there was another thing that I didn't know, that then we went computing the trace of the stress tensor in the boundary, and we found that it was not 0. And we were a bit confused of what was happening, and we found this expression that comes from holography. But then, searching a bit, we discovered that, of course, this was well known. We didn't know, but people knew. And the reason why is that Maxwell theory in dimensions which are not equal to 4 is not scale invariant. Sorry, it's not conformal invariant. It's only scale invariant. So if you take field theory, Maxwell, in 3 or 5 or 6 or whatever, what you will find out is that the stress tensor trace does not vanish, but is actually equal to the divergence of a current, which is called the virial current. And this is a famous result of this gentleman down there. And you recover exactly the same expression from holography, which is something nice, because it means that the boundary condition that you're actually putting makes sense. You are actually getting what you should get. So this was a nice surprise to us. And then let me express just very quickly question. Yeah.
Could you go back to the slide about the boundary condition? One slide before. Yeah. So in your boundary condition, you have omega and k. And can you explain what are they? Are they omega and k of what? Do they
So yeah, so omega and k are basically frequency and wave vector of the fluctuations that I have.
Of the perturbation you have on the boundary.
Yes. So these are the frequency and the wave vector at the boundary. So I'm basically going to, so if you like, I'm writing the boundary condition in Fourier space. So if you write them in Fourier, if you don't write them in Fourier space, you will have a bunch of, you know, derivative with respect to space, boundary, space and time. And if you write it this way, you can just get frequency and the wave vector. Now, another thing that I didn't say, but is important, is that you get also these weird factors and these things. These Z that you see there are not exactly the gauge field, are gauge invariant combinations of the bulk field. So there are a bit of subtleties here and details that I just kind of skipped, but you can find them all explained in the paper if you're interested, or I can explain more after.
And when you are interested in the general dynamics of the gauge field on the boundary, I mean, which will be realized by superposing many Fourier modes, what kind of boundary condition are you going to do we need to?
Sorry, I didn't understand. Can you repeat?
I mean, in using this boundary condition, you'll be able to describe the dynamics of one Fourier mode of the gauge field because you have only one omega and k. Okay?
No. It's more than that. You will see.
More than that.
Yeah. So all these Z, etc., are also function of omega and k. So the question that you will get at the boundary will be a function of omega and k, which will be quite complicated.
Right.
Yeah. So you will see, you will find much more than one mode. So yeah, let me just explain 1 second, very briefly, what I mean by magnetohydrodynamics for those of you who maybe are not so familiar and they're more into the holographic part. So as I said, magnetohydrodynamics is just the low energy effective descriptions of a system with a dynamical U1 gauge field, so dynamical electric field and magnetic fields. Now, depending on who you talk with, magnetohydrodynamic is, is defined in different ways in the sense that there is an important and subtle distinction of how you count electric fields and magnetic fields in the sense of orders. And I'm not going to do anything like that. So here I will count basically everything order 1. So sorry, the opposite. I will count the electric fields as order derivatives and the magnetic fields as background. This is usually the standard description of the standard assumption here. I'm not going too much into the detail, but I can be more precise after if you want. So this is basically the standard, let's say, procedure to construct an hydrodynamic theory, at least in the standard form, like without using an action formalism or an entropy functional, etc. So one starts from the question of motion. So the question of motion comes just from the symmetries of the system. So these are basically, in our case, the conservation equation and basically the Maxwell equations. And then what one does, one write down the constitutive relations. So we do basically a gradient expansion, which is an expansion at late time and long distances, and one starts writing all the pieces which are allowed. So this is an effective field theory. So everything which is allowed should be there. And you start writing down. So here I just brought down the formulas for you, at least at leading order for the stress tensor and the current. There are subtleties again. There are many subtleties related to the choice of frame and the blah, blah, blah. I don't want to enter there because that would be a talk by itself. And I'm not expert enough to say, anything very meaningful there. But so here, what you see, these are the constitutive relations that we use. The first pieces are the equilibrium. So for example, you can see energy and pressure. And the second one are basically terms. So the capital pi and the nu are the dissipative terms. So these are terms that enters with ordered derivatives. And then what you do is you plug this constitutive relation into the equation of motion. With a bit of trick, this becomes a big matricial problem. So it's a matrix times, basically a vector of your excitation. So the vector are all the hydrodynamic fluctuation, the hydrodynamic degrees of freedom. You can see the fluctuations of the temperature, of the velocity, electric field, magnetic fields, etc. And this, of course, depends on the system you have. And then in order to find out what are the excitations, so if you are interested only in the excitations, you want to find the dispersion relations, and you're not that interested, for example, in green functions or stuff like that, then it's easy. You take this matrix, you impose the determinant equals 0, and you find all the eigenvalues. This is just an eigenvalue problem. And the solution of this eigenvalue problem will give you the frequency in terms of the wave vector. And you can see already here, back to your question, this matrix, the rank of this matrix basically will determine how many excitation you'll have, basically the space of your excitation. But in principle, if you don't truncate this series, you will have infinite excitation. So this matrix become an infinite dimensional thing, which of course you cannot treat. So most of the time in hydrodynamics, you truncate to first order, which is what I do there. And then you get only a bunch of modes up to the dispersion relation of those modes, you get it only up to the 2 order. Okay, in orography, in principle, you don't need to do that, and we don't do that. So in orography, we will solve an equation which is similar to that equation over there, where the determinant is 0, but we don't do any truncation. So in principle, numerically, you can compute the dispersion relation as a function of a wave vector for all the possible modes, not only the low modes, and for all possible wave vectors. This is just a numerical game, if you like. Oops. Yeah. So let me go a bit to what do we get. I'm being very slow. Okay. Anyway. So let me start from something which is very well known to show you that actually we get what we should get. So if you follow magnetohydrodynamics and you check, for example, a system at 0 density and 0 magnetic fields, what do you find? So at 0 density and 0 magnetic field, the stress tensor decouples. So the stress tensor dynamics is basically trivial. There's nothing interesting, so I'm not going to show it. But there is another sector which is more interesting, which is basically the gauge field and the current dynamics. So electric field, magnetic fields, and charge. And what you find here are the equations that you get a linear order. So the equation on the left is an equation that all of you should know. It's actually the equation for electromagnetic waves in matter. So if you switch the sigma, which is actually the conductivity, to 0, you get the equation for basically a photon in vacuum. If you have matter, so if you have a system where you know that the electric constant is non-trivial and you have some conductivity, then you find these equations that usually in the electromagnetic textbook is solved imposing the wave vector to be complex and the frequency to be real. And that's what goes under the name of skin effect. So this is basically what determines the penetration of electromagnetic waves into a material. In our case, we want to solve it the way around. So we want to keep the frequency complex and the wave vector real. And you will see immediately what this gives. And on the right, what you see is, on the contrary, what in a theory with no dynamical gauge field is charge diffusion. But now, because you have a medium and the gauge field is dynamical, there is screening. And therefore, you can see the charge actually does not diffuse anymore, but it's damped. And the rate of this damping is actually given by basically the strength of this electromagnetic interaction. And indeed, you see that one important thing here is this ratio sigma divided epsilon e. And you can see the sigma divided epsilon e, at least at low lambda, grows like lambda. So it becomes more and more strong in increasing the strength of this electromagnetic interaction at the boundary. And that's expected. And these are basically the modes. So these are numerics again. And you can see that you can compare the hydrodynamics. So one thing that I want also to clarify is that all this quantity here that you see, like these susceptibilities, conductivities, and all these things, can be computed independently. So I can basically solve this equation without computing any quasi-normal mode at the boundary. And then I can compare. And if I compare, that's what I get. So you see, blue line is for lambda very small. And it's what Shin was saying before. So you are approaching the limit of the photon being decoupled. So the interaction with matter is very, very mild. And you have basically almost a photon. And then the interaction with matter increases. So the screening effect becomes larger and larger. And this photon is thrown away. And what you see is basically a diffusive mode at low frequency, which is nothing else. In magnetohydrodynamics, this is again very well known, is the diffusion of the magnetic charge, magnetic flux, if you like. So for those of you who are interested in more in magnetohydrodynamics and desire form symmetry, this picture can be understood very easily in the iron form symmetry in this way. If you consider Maxwell equation, there are actually two global iron form symmetry, one electric and one magnetic. The electric one counts the flux of electric field, and the magnetic one counts the flux of magnetic fields. Now, the flux of electric field is not conserved whenever you have charges, because electric lines can end on charges. And that's exactly the reason why one of the two modes become non-hydro. So basically, the imaginary part of the non-hydro mode that you see there is nothing else than the statement that the electric flux is not conserved anymore because you have electric charge. But there is one symmetry which remains, which is a conservation of magnetic flux. And that's exactly, that symmetry is there as a conservation equation, and the diffusive mode that you get in the limit of large lambda is exactly the diffusion of magnetic flux. Okay, so this is a different interpretation that I want to share with you if you are more interested to that side. Now, of course, I'm going to be a bit fast here because then you are seeing already where I'm going. I'm going to show you that basically all that you expect from magnetohydrodynamics will match what you expect from holography. So in a way, you could say this is kind of a trivial check, but it's an important check to verify that actually what I'm doing is correct. And you can carry on. Of course, you can start making these things more complex. So for example, here I can switch on a magnetic field, and you see that basically all the dispersion remain the same. There is one funny guys, which is these magnetosonic waves. The magnetosonic wave is very similar to standard waves in, say, a charged fluid, with the difference that it carries also magnetic flux. So it's not just pressure wave, it has also some magnetic flux attached. And again, you can see the dispersions of these modes. I'm not going to explain too much, but what you have to think is that every time you see a line, this is basically what the magnetohydrodynamic theory is telling us. This is an independent computation, it's not a fit. And the dots are the numerical results. So these are the numerical results. And of course, you can see that at least in the regime of small frequency and small momentum, hydrodynamics works. So notice that when I say hydrodynamics works, I always mean linearized hydrodynamics. And that's exactly the reason why it works only there. In principle, if you're strong enough, you can push these magnetohydrodynamics to higher order, and you will find better and better agreement, hopefully, up to a certain point.
Do you have any qualitative difference between the magnetohydrodynamic theory and holography?
Qualitative difference?
Qualitative.
In the regime where they should agree, no. We actually find that magnetohydrodynamics works perfectly where it should. We actually find, as always in holography, that it simply works better than it should, which is, I will comment a bit at the end. So there is one limit, which is, there are two limits which are tricky. So one limit is the large B limit, and the other limit is the large lambda limit. These are the two tricky limits, and this is actually where I believe that holography can be helpful, because the small B limit and the small lambda limit, as you see, you don't need holography. I mean, you can do magnetohydrodynamics. If your magnetohydrodynamics theory is correct, you will get everything. But there are certain limits where, I mean, we have people that know probably more than me here, but in the magnetohydrodynamic community, the large B limit is a tricky limit. And there is still debate whether people forget some terms, how to count certain things and some effects. And I believe that holography here can be helpful because the holographic theory is there, and it's just a matter of exploring now what to do. Yeah.
Also, in the case of holography, so you can discuss the effect of higher order excitations, like for the case of, say, quasi-normal mode holographic calculation versus hydrodynamics. The quasi-normal mode calculation also has the higher decaying non-hydrodynamic.
Yes, exactly.
You also have that kind of non-magnet hydrodynamic mode in your calculations.
You mean from the magnetohydro part?
No, for your holographic calculation.
Yeah, in holography, for example, look at those modes over there. Like the green mode is definitely non-hydro.
Okay, I see.
You see?
Yeah.
So that's a non-hydro mode. Is actually, again, you see, to be fair, yeah, okay, now we go back to language. What I call magnetohydrodynamics contains actually a lot of non-hydrodynamic modes.
Okay, I see.
So we have to be careful what we call hydrodynamics, because the moment you put U1 interaction, you gap out a lot of stuff. Now you will see, as you expect, that if the gap is small enough, you still capture that thing. And that's also a big question, right? In the context of quasi-hydrodynamics and all these things, you have quantities which are not conserved, but they are almost conserved. This can happen in many situations when the symmetry is softly broken, close to phase transition, where you have ordered parameters that become soft. So this is a very big topic, both in condensed matter and in QCD or nuclear thing. And indeed, that's another place where holography can play a role. So we didn't study too much the quasi-hydrodynamic structure here, but you can study it. And of course, it can tell you also a lot on when you will expect hydrodynamics to collapse, which by itself in the hydrodynamic picture, you don't have a clear idea. You can make some, estimate or whatever, but I don't think it's that clear. Well, so since I don't know what time is it, but I feel like I'm extremely late. Let me just skip very quick this. So this is to tell you that indeed the theory works, things become more complicated. You see that hydrodynamics dispersion relation becomes complicated. You still can compute all of these independently. These are all just susceptibilities. They look ugly, but they're not that bad. And you see more and more effects. For example, you see that the plasma frequency appear. You can check that actually the plasma frequency formulas is what you expect. And the plasma frequency, of course, grows with the coupling, with the screening, and that's all expected, nothing so special. And again, these are modes, and these are hydrodynamics. You can see back to the question of Taka, these modes are not hydro at all, but still the hydrodynamics or whatever you call hydrodynamics capture it well, but you can see that the order, you see this omega divided T, this is still, these gaps are very small. Now, if you push, I think I have a picture at a certain point, maybe not. No, I don't have a picture, but of course, if you push this higher, hydrodynamics then would be completely out. That's clear. So back to your question, the question of Shin, this is what happens if you take the lambda equals 0 limit. So if you take the lambda equals 0 limit, you get a pure photon, which is what we were saying, because basically you are decoupling the photon from the matter. There are some subtleties about the interpretation of what this means, especially in the context if these photons really belong to the CFT or it's just something decouples. And I'm not going to enter too much. There is a nice paper about that if you're interested, I can mention at the end. But okay, this is the summary of part 1. That's why I accelerate a bit, because I want to say at least something about part 2, which I think I use already more than the time for my talk, but I can speed up. So the summary of part 1 is that if you use Maxwell and Higgs boundary condition, you get magnetohydrodynamics. Now, at this stage, we wanted just to prove this statement and that there is no need of higher form symmetry. And but of course, as you guys, are the sharing was lost? I touched something. You don't see it anymore? Oh.
I did that before. I touched that one.
I see. But nobody complained, so I just did it now, no? My bad. Okay. Okay. Sorry about that. So yeah, that was the summary. So here there are a lot of things to do. We already discussed a lot. So let me go quick and then we can maybe discuss after offline. Then the second part that is kind of obvious is you want to add this to the superfluid and get a superconductor. And that's what I mean by sitting X on the boundary of ADS. Let me be very fast. I already mentioned there is this paper and a very famous paper. This is supposed to be a superconductor. It's not a superconductor. And again, let me also say a disclaimer that, you know, superfluid and superconductor for many things are very similar. But of course, for certain things, for example, collective excitations are not at all. And I don't think I need to describe this too much, but just very quickly, difference between superfluid and superconductor. The main difference that I will be interested in is the last row. And in particular, we know that for superfluid, we have a Goldstone that appears. This is this massless mode that then coupled to the rest and creates second sound. And for a superconductor, there's nothing like that. There is a massive gauge field, which is this Meissner effect. And this is exactly the reason why this magnet is floating around. It's basically repulsion of magnetic field. And so I want to just convince you that there are different systems. Of course, they share many similarities, but they're different systems. And of course, as probably you know as well, there are effective theory description that can be done. The simplest thing is just this superfluid Gibbs-Landau, which it's just a very simplified and effective way to see what happened, but it works pretty decently. And then, of course, one can do more. One can do the full superfluid hydrodynamics. How you do that? Here I sketch it just in the case of probe, so no stress tensor. You have your conservation equation, and you have to add a new ingredient, which is this Goldstone. Usually is repackaged in what is called the superfluid velocity. It's the derivative of the phase of the order parameter. Remember, the amplitude of the order parameter, it does not appear because it's not an hydrodynamic mode, at least far from the phase transition. Then you do the same game. You have the constitutive relation. You have another equation, which is called Josephson relations, that comes out from basically the fact that the Goldstone is the dual fields to the charge density. So you can use basically the commutation rules, and you get this Josephson relation. It's not so important, but the important thing is that superfluid hydrodynamics can predict a huge amount of things. It predicts that there is a sound mode. It predicts the infinite conductivity. And if you extend it, it can be extended. And what I want to tell you is that a few years ago, we actually proved that the superfluid hydrodynamics with also the stress tensor captured completely all the modes of the original superconducting paper. So if you take the Arno Horowitz Herzog paper, you do the full quasi-normal mode with back reaction and everything, you see that the hydrodynamics works perfectly. Okay, and they're even close to the phase transition. So there's absolutely no secret. That is a superfluid, and that's perfectly captured by superfluid hydrodynamics. So that's the first statement that I want to make. And the second statement is that, of course, if you want to now put dynamical gauge fields, you can get some intuition from Gibbs-Landau. What you do, you just introduce your Maxwell term, you couple the derivatives, now becomes covariant derivatives, and you do the same kind of trick, and you find almost immediately two important things. One is that there is no Goldstone anymore because it's eaten by the gauge transformation, and as a consequence, the photon become massive, and that's the equation that you get over there. So you get this equation on the bottom, where basically this parameter lambda Gibbs-Landau, it's if you want the mass of this gauge field in particle physics language, and this just is equivalent to the penetration length, if you like. And this is nothing else than the equivalent of the Anderson Higgs mechanism. Nothing more than that. Now the question is, can we get that? Can we get this Higgs mechanism and all of this? And the answer is, of course, yes. And what we wanted to do, we took the standard holographic superfluid model with the boundary condition that I discussed. And again, let me emphasize that we are not the first to do that at all. There are a huge amount of paper. And our focus was really to show the collective excitation and to study the collective excitation. In particular, we were interested in studying the Higgs mode. So you start doing that, and you discover, you start doing this analysis. We started from the transverse collective mode. And what you find here is that the same kind of equation that we had before now is slightly modified. There is a mass terms that comes out, and these mass terms, you can see, is basically this mode become massive. And the important thing that I want to emphasize is that you can check that this sigma is indeed the conductivity. So once again, you see on the left, basically these data are the numerical data, and the line is the line of the conductivity, which can be obtained from the the corresponding Kubo formulas. On the left, you see the mass of this transverse mode that, let me call it electromagnetic waves. And you see that this mass is quite interesting because at very low temperature, it becomes exactly the plasma frequency. So you see this line that I draw is not a fit, again, is the expression for the plasma frequency. You see a low temperature is the plasma frequency, but we also know that at a certain point, this mass has to disappear because this mass comes because of basically the superconductor, if you want, the phase transition. And you see that indeed at the critical temperature, it vanishes. It vanishes with the typical critical behavior. And this again is a critical behavior that can be understood with Gibbs-Landau and can be also derived doing perturbative computation in holography close to the phase transition. So that's all nice. And actually, yeah, that's Makoto in his recent paper as an expression in terms of bulk quantities. So you can see on the left, this is basically an expression for this mass, which is obtained by perturbative computation close to the phase transition. And you see this psi there, and these things are all bulk quantity. So you integrate this bulk quantity, 0, 1 is just boundary and the horizon, and you get this quantity that is called high. And the lambda, again, this is, I basically rewrote Makoto formula in our language. So lambda for us is the electromagnetic coupling, actually square. And you get this formula, okay? And which corresponds basically to the Gibbs-Landau, that's the point. And you see this formula works great. So you see that the formulas of Makoto is basically the line, the dashed line, and the rest are numerical data. And you can see that indeed close to the phase transition, so to critical temperature, this formula works very well. And then, of course, if you go to lower temperature, this formula starts to, to not be anymore a good approximation, and the numerics go somewhere else. And on the bottom, you see also that these different colors are different strength of the electromagnetic coupling. And you see that independently of the strength, close enough to the phase transition, that formula works. That's great. So then you can go to the longitudinal collective modes. So here, I have to be honest. We didn't perform a full hydrodynamics or effective field theory description. And the reason why we didn't is that it's not that straightforward. The reason why it's not that straightforward is that if you start from hydrodynamics, one has to include the order parameter inside. So you have to enlarge superfluid hydrodynamics and add the order parameter, which becomes extremely important close to the phase transition. And then you will get something like quasi-hydro. So for those of you, for example, who are QCD people, this would be kind of similar to hydro plus. It would be the same kind of approximation. So you really need to add a slow relaxing mode close to the phase transition to get the correct physics. And if you start on the contrary from, let's say, some Gibbs-Landau or some field theory effective description, then you have to incorporate all the dissipative terms. So you have difficulties in both sides. I don't think it's impossible. It's just we didn't do it, but that's something that would be nice. But all of this is to say that these equations that I wrote down are basically phenomenological equations. So these are just intuitively written down, coming from some Gibbs-Landau intuition, but they're not derived from a very formal, hydrodynamics or field theory perspective. I'm not aware of anything like that. It would be actually interesting to do something like that. Also, maybe from the point of view of Hohenberg and Alperin, classifications and stuff like that. Now, what happened to the superfluid sound mode? So to the superfluid sound mode, which is the mode on the top left, actually, yeah, let me say something about the physics. So the one on the top left is what in a superfluid would be the second sound. The one on the right is what in a superfluid would be the order parameter or the amplitude or the X. Sometimes they call it X. So what you see is that the guys on the right is not really affected. Okay, and on the contrary, the guy on the left is deeply affected by the fact that the gauge field is dynamical, and I underline with the blue line the terms that appears because of that. So if you remove the terms which have the blue line under, you get the dispersion relation for basically the second sound mode, where gamma is the attenuation constant of second sound mode, and v is the velocity of second sound. Indeed, interestingly enough, if you fit, you find out that this gamma and v are exactly the gamma and v that one finds in the superfluid model. So these parameters are actually not affected, at least a linear order in lambda, and you can see the three different colors are three different values of the electromagnetic coupling, not too large, and you see they all overlap with each other. So they don't depend, it doesn't depend on the electromagnetic coupling. On the contrary, the other two parameters are again the parameters that we know, and they coincide with exactly the same parameter in the transverse sector. So one is the same conductivity that I was talking about, and the other is the mass. So again, is it surprising that the mass is the same? Of course not, because what gets the mass is the full gauge field. And of course, both the transverse and the longitudinal component, they have the same. So this is one thing. Now back to our X mode. So what was my problem, or let's say my question? My question is that if you think about the holographic superfluid model, you don't see any mode that become massive. But if you think about Gibbs-Landau or some effective description, the first thing they will tell you is that if you have a superfluid or whatever, you should have some X mode that becomes massive at a certain point. And my question was like, what is happening? Why there's nothing massive going on there? And the other question was like, well, does this depend or not on the fact that this is a superfluid rather than a superconductor? And so we did the same exercise with the superconductor. So what you see here is what we call X mode. And let's start first on the right. So on the right, you see that if you go at low temperature, you see that there is a mode which becomes massive. Now, this is this red mode. So this red mode acquired a finite real part and the massive, and it starts like to approach like a constant value of 0 temperature. Now, why I didn't push it too much? Because we are probe. So we did probe limit, so I didn't show too much because basically there's no reason why you would believe so low temperature. But you clearly see, what you clearly see is that these modes appear from a collision with something which is non-hydro. So there is a kind of crossover between something which is highly overdamped, which is basically above, say, TC06. Sorry, T over TC06. The dynamics is highly overdamped because there is a green mode which is as a real part, but you see this green mode is extremely damped. It's very non-hydro, so you can forget about the green. And the blue has 0 real part and a very large imaginary part. So this mode is overdamped. And there is another mode, which is the black, which has 0 real part, but finite imaginary part. So basically, close to the phase transition, the dynamics is completely determined by the black mode, but the black mode is a purely imaginary mode. That's exactly what you expect close to superconductor, where the order parameter fluctuations is a slowly relaxing mode. But then there is a kind of transition, this overdamped mode through a collision becomes underdamped, and it gets a mass. So there is a collision with a second mode, and then this guy becomes real. So it's very tempting to think about this as the X mode. And indeed, if you do some, I didn't show it. Well, actually, you can. Let me see. No, I didn't put it, but you can show that also with Gisborne-Landau, you can get something very similar, even if it's not exactly the same. So it would be nice to have a full description of this. Now, let me just compare something. After I sent the paper to some friends, they actually told me that there was one paper discussing similar stuff for holographic superfluid. This is this paper, quite old, by Stoner and al. And what they claim here is that there is also here a kind of overdamp to underdamp crossover, but the dynamics is completely different. So let me guide you here. So this is the holographic superfluid model. And what you can see on the top is basically a sketch of the modes at finite wave vector. So let's start, sorry, not a finite wave vector, at 0 wave vector. So C is the normal phase. So in the normal phase in C, what you see is that there are 2 scalar modes, which are very close, are the critical modes, the one that will go to 0 to the origin at the phase transition. And then what happened is that at the phase transition itself, one mode will go to the origin. That's what will become the sound mode, or a pair of mode, if you like. But one of the other will go down. This is the order parameter fluctuations that will become slightly relaxing. And then there are still other 2 which are completely non-hydro. But you see what happened. If you decrease even more the temperature, at a certain point, there are 2 other modes that crosses this mode, which means that the relaxation at late time will be now not dominated by the order parameter, which is on the imaginary axis, but will be dominated by these 2 modes. Now, why I'm saying this is very different? Because you see the sound mode is still there. You see the red mode is still there. So this is not what you expect as a X mode in a superconductor. There is still a kind of real mode that appears there. So my claim is that this holographic superfluid picture does not encapsulate any X mode, at least in the standard language, while when you do the holographic superconductor, you see something that reminds a lot of that. Now, and this is basically what you get at low temperature. So you see the massive mode, and you see the imaginary part. And the lines are Gisborne-Landau theory. So again, Gisborne-Landau theory captured this quite decently. And this is basically a picture more of the crossover. Actually, this is the slide that I wanted. So the formula that you see on the top left, it's Gisborne-Landau theory. Okay, so you see that there is a mass, which is given by this parameter B, and B and A are basically the parameter in the Gisborne-Landau effective, the Lagrangian. So are the parameter of the, now, let me, here. So A and B, B is the parameter that change sign, so the one that goes to 0, the critical temperature, and A is basically the susceptibility. It's basically the mass density, the inverse of the mass density. And you see, this is what you get from Gisborne-Landau. Now you solve this equation at 0 wave vector, and you get basically the picture on the mode on the top right. So you see this mode is indeed doing exactly what I was saying. So close to the phase transition, omega h is small because B goes to 0 at the phase transition. So this means that close to the phase transition, that mode is a couple of two imaginary modes overdamped. They're both imaginary with different imaginary parts. And then at a certain point, obviously, when the square root becomes 0, they collide. That's the crossover between underdamped and overdamped. And below that, you find that basically one mode, well, both modes get the real part and the constant imaginary part. And at least in our model, this happens around TC half, which is quite interesting because some estimate in real material, real superconductor give a similar estimate. And an interesting aside is that this gamma doesn't look like to vanish at 0 temperature, which is kind of weird because usually dissipative terms vanish at 0 temperature. This doesn't, but I don't have a clear answer to that. Another thing that I want to say, which is interesting, is that the X mass recover the Gibbs-Landau scaling. So if you take the ratio between these two mass, you easily find that this is 1 over square root lambda. And there is a nice explanation coming from Gibbs-Landau that actually Makoto explained to me. And it's very beautifully encoded in the holographic picture. One puzzle or one interesting thing is that if you compute actually the ratio between this X mass and the gap, the superconducting gap that can be extracted from the optical conductivity, you found that this ratio is extremely small. So in BCS-like theory, you expect that this is basically equal to 2 delta, the mass of this X mode. In this holographic model, at least you find that this is much, much, much larger, smaller. So I don't know what to say about this. It's interesting. I don't know if there is some physics, if it's a signature of strong coupling, if something is signature which is not BCS physics, I don't know. But it's a fact. It's something that we should think about it. And let me finish because I'm very over time, I think. So the other thing is that, of course, we verified through the analysis of the collective modes that indeed this boundary condition with the holographic superfluid model are, well, represent an holographic superconductor in all senses. And I think there is a lot to do also in terms of effective description to understand better these dynamics. Let me just say a few things for the future. So we now learn how to put dynamical gauge symmetries in the boundary field theory. Let me also mention that there are recently many papers, especially also one from Japan, since I'm in Japan, of Maeda and friends, where they manage actually to do the same game with the graviton. So you could do the same game for the graviton. Usually if you put Dirichlet boundary condition, there's no gravity at the boundary. You can play similar game, and then you get basically Maxwell Einstein equation at the boundary. And you can use them to do cosmologies. So to my understanding, the first people that did that were David Mateos and collaborator a few years back. But recently there are a couple of papers, one by Kiritsis and collaborators and one by Maeda and collaborators, where they do that. And this is to say that this kind of dynamical gauge fields at the boundary, they can have a lot of applications. I focus more on condensed matter and magnetohydrodynamics, but it could have an impact on many more fields like UCD cosmology. So if you really want to use these holographic tools for some gauge theories where the gauge dynamics is important, you don't want it frozen, then you need to do something like that. And then there is something also very interesting, which is more formal, which is this relation with higher form symmetries and how really symmetries are realized through boundary conditions in the bulk and in the boundary, which I think it's interesting. And one thing that I'm particularly interested in here is the role of, rethinking about the role of gauge and global symmetries in the bulk and how they are realized at the boundary. So I think I spent even too much time, so let me just finish here. Thanks a lot for everyone here and online for listening, and I'm open for more questions.
Okay, thank you very much for a nice talk. So are there any questions or comments?
So you mentioned that you can extend this construction to the bulk dynamical graviton. Is it in which dimension did they do that? Is it 4-dimensional bulk or 5-dimensional?
I believe that they want to study real world, so they have 4-dimension in the boundary, and they want to do cosmology. So actually, one of their task, at least of some of the paper that I read, is to do cosmology. And therefore, they have 4-dimensional world in the boundary and ADS5.
Is it introducing some UV cutoff plane? Did they consider
no, I
random
think-
construct on the plane?
Okay, I cannot say much because I just scroll it fast, this paper. I can send you the reference, definitely. I don't remember any cutoff.
So they introduced the dynamics of the graviton by changing the boundary condition?
Yes,
Oh, really?
yes.
Oh, really?
Yeah, again, the details, I don't know. So I don't know if any, I'm not sure if anybody know, if anybody here knows, can say something, but
Yeah, as you know, in 5 dimension, the leading part of the bulk gravity perturbation is non-normalizable. So it's weird.
yeah, I'm not sure how they do it.
Yeah.
Maybe they just put a cutoff, I don't know.
Yeah.
But that's a good question. Indeed, I remember that the first time this was tried was a long time ago, and they tried to do it with leaf sheets to change the, so that's exactly what you were saying, that you use leaf sheets so that you can change the normalizability and whatever, and then you can have dynamical gravity with leaf sheets though. But yeah, I don't know the details. I will send you, I mean, I can show you the references and you can have a look.
All right. Thank you very much.
Welcome.
So I have a question. So at the very beginning of the holography appeared, people discussed whether the CFT is UN gauge theory or SUN. The difference is the presence of U1 or not. That so in this case, can I understand that the UN n equals to 4 superions can be decomposed into SUN plus U1, and that U1 part is your dynamical U1? Maybe my question doesn't make sense, but
Yeah, I don't think I know the answer. Maybe, I don't know. I never, let me say, I never thought it in that way. I don't really know. So what I was thinking here is more like in terms of effective description, not really like n equal 4 or whatever. I was thinking about having a system with a conserved charge and the global U1 and make the U1 dynamical with a gauge field. Without thinking too much if this is n equal 4 or this is whatever. Of course, if you take, you know, some Schwarzschild or Einstein gravity, this should be dual to some n equal 4 or whatever, but I don't know in terms of microscopics.
so the question comes from the fact that the original D-brane picture is that we have n D3 branes.
Yes.
On that D3 branes, the gauge group is UN. It's not SUN.
Yes.
So if we naively take the dual, then the field theory side should be UN n equals to 4 superiors. But the people found that the dual theory is not UN, but usually it's supposed to be SUN. Then I can find the explanation why it happens is that if we had a U1 part, then it cannot be free because it interacts with everything. I mean, in the gravity side, everything interacts. So this is one explanation why that U1 part is decoupled after taking the near horizon limit and so on. So I'm confused now. So you can introduce the dynamical U1 gauge field. So, well, my naive question is that are there any relationship between that theory and what you have done here? Maybe. No idea.
I'm not sure.
I'm sorry.
I don't see it
Okay.
now.
Okay.
I don't know.
Yeah.
Can I make a comment?
Yeah.
Of course.
Okay, please.
Well, as you know, n equals 4 superion mills has a R symmetry. And I believe what we are doing is to gauging the global R symmetry.
Okay. So this is the interpretation.
Oh, yeah.
Oh, I understand.
That's my guess. Yeah.
Okay, thank you very much. So any other questions? Okay.
So in the language of higher form two-form fields, what kind of boundary condition were you imposing? So in the language of Maxwell, you were imposing mixed boundary conditions. What kind of?
Yeah, so that's
for-
a very good question. So let me go back to, so again, your question is like, well, the answer to your question is, it depends what you want to do. As you see, you know, depending what kind of physics you want to get at the boundary, you impose different boundary condition. Now, if your question is what kind of boundary condition you impose for the higher form symmetry to get the same of what I said, the answer is simple, it's the Dirichlet boundary condition with a caveat of dimensions. So if you actually do it in, I really suggest, if you're interested in that, to read this paper, because there are all the details there. But you see, this is kind of the map. So if you take this, what they call magnetic gauge field, which is our two-form or higher form, then regular boundary condition corresponds to dynamical U1. Of course, you can do the opposite, and you can get also global U1, but then, so in a way, if you like, if you are just comfortable with regular boundary condition, if you want to do global U1, you use the electric gauge field, and if you want to do dynamical, you use that. But the point of our paper and my talk is that in principle, you don't need to do that. You cannot forget about this. And you can just use this with different boundary condition and you will get exactly the same, which is exactly also what this diagram basically show. Now, is it one more convenient than the other? Probably depends on which kind of physics you want to do. For example, for the question that was asked before about coupling to matter, I'm not sure. It might be quite different story. From the bulk perspective, it's the same thing. But this kind of question, I think, is very related to, again, think about particle vortex duality. Depending, one phase looks one way in one language and the other way in the other language. Is one language, better than the other? Well, probably depends which phase you want to describe. If you want to describe a vortex, then probably the dual description is, much more, easier if you want. But the physics should be the same. Of course, the realization in the two languages can be very different. So I don't want to make a big statement, but in my understanding, I don't think this higher form symmetry or higher form language adds any physics. It's just a convenient rewriting or reformulations in terms of dual thing, which in some limits can be more convenient. But I don't see how a dualization or whatever can introduce more physics. But I might be wrong, I don't know.
Any other questions, comments?
May I ask a question?
Yes, please.
So in the first part, you explained that you can formulate a magnetohydro without relying on the higher form symmetry. But if we use a higher form symmetry, because it is global symmetry, we can only we can focus on the gapless mode, like the magnetosonic or Alfvén bond anyway. But if you use the kind of the conventional formulation, including the Maxwell equations, your theory also contains a massive excitation, like described by electric field, as you show. And is it possible to just focus on the gapless mode in this kind of the dual formulation without relying on the higher form symmetry? So
let me see if I understood completely your question. So you are saying that in this gauge field, well, in the formulation that I have, I can capture all the modes, including the modes which are non-hydrodynamics. Yes. And you are saying that if I use the higher form description, I cannot do that. Yeah, it can. Yeah, you can do that because if you introduce also the electric flux as a dynamical variable, you can also describe both a non-hydrodynamic mode and the true hydrodynamic mode. Yeah, so I don't think I got your question. Then what's the question? My question is that so in this kind of the conventional approach, without mentioning the higher form symmetry, yes. Can you restrict yourself to the gapless mode to try to find the true hydrodynamic mode? I mean that here you have the Maxwell equation too, so that the resulting dispersion relation contains a gapped electric field. Yes.
And
yeah, so
yeah.
I think that the answer to your question is as follows. So this theory that I have here gives me everything. So all that dispersion relation analytically, and then I can basically throw away the modes which are non-hydro. Now you have to be very careful because we are truncating the theory at a certain point. So this theory will give you a lot of non-hydro mode. You have to be careful which one you trust and which one you don't. So in the limit where, for example, let's consider, for example, the electric field that you mentioned. So if the electric field, if I make the screening very strong, the electric field fluctuation becomes very non-hydro. So the moment that they become very non-hydro, I can simply integrate them out. So they basically disappear from the hydro. And then my hydro simplified a lot because basically the fluctuation of the electric field are completely out. And the reason why is because this non-hydro mode will go so far away from the hydrodynamic regime that basically the hydrodynamic regime description doesn't need this non-hydro mode. Now, when you are in a situation where these non-hydro mode are kind of close to the rest, it's a bit more tricky. You cannot simply integrate them out. I mean, you can, but then you have to be very careful. They're not massless, so you don't find any divergence or IR divergence, but it's a bit tricky from the hydrodynamics perspective. Now, I'm not so expert in the magnetohydrodynamic perspective to say something very big. From the holographic point of view, basically, you cannot, because what you can, holography gives you all at once.
I see.
So that's also the power of that, right? Because in the magnetohydro or in hydro in general, if you have non-hydro mode, you have to be very careful because once you are truncating the series, you can get mode that looks like spurious. And
I see. So you mean that in the holographic approach, your action and boundary condition includes all the information, including the massive excitation. So you can restrict yourself to the, how to say, the desired correlation function to extract.
Yeah, exactly. It's just my choice to restrict to something, but the theory is not restricted by anything. So that's why, in a way, holography, it's much more general or larger as a theory than hydrodynamics. It's not just hydrodynamics. There's much more than hydrodynamics. There are all the modes, and I don't need to restrict to low frequency, to low wave vector, or to low gaps. The theory gives me everything. It's basically like a microscopic theory, if you like.
Okay, I see.
And that's also why, can be useful because, in my perspective, for hydrodynamics theory, there are two ways in which it's useful. The first one is that writing down a hydrodynamic theory when you start breaking symmetries or making system complicated is difficult. So it's easy to forget terms or to, mess up with something in constitutive relation or in redefinition of frames and blah, blah, blah. And holography here can help you because, for example, it happened because I was working on the same things for translations, and we found out that the hydrodynamic for charge density waves was missing a piece. So how we realize, we build a holographic model, we compute the modes, we check the old hydrodynamic theory, and the old hydrodynamic theory was not working. So we was not in agreement with our modes. And we were saying, okay, well, what happened? We check our computation, we check again, our computation is correct. So what was missing is that the old theory of charge density wave in presence of pinning was missing a term. And that's one way that holography can be useful. Like, of course, that term didn't need holography to be derived. It could be derived from hydrodynamics, but because of the complications, it was not put. The other thing is that magnetohydrodynamics, or all this kind of effective approach are effective. And of course, they have some limitations. They have a regime of applicability. And holography can go much beyond that and can also try to explain what is the regime of applicability of these theories. And finally, as you well know, all these coefficients that, for example, you see here, hydrodynamics cannot compute them. So holography can tell you all the dependence of this coefficient in terms of temperature, pressures, and blah, blah, blah. And then you can compare to your favorite microscopic model, which could be, I don't know, kinetic theory or some field theory or whatever simulations you have in mind.
Okay, thank you very much.
Welcome.
And so I have also another small question, just for the curiosity. And in the second part, you showed that the kind of the analysis for the holographic analysis for the superfluid system.
Yes,
I think. And I think this is holographic model of the relativistic superfluid, I guess.
Yes.
And do you have the can you describe the non-relativistic superfluid relying on this kind of the holographic language?
Very good question. You can, and indeed, if you come Friday at Riken, I will share a puzzle about that. So you can. So you can basically go to situations in which instead of the full Poincaré group, you break the Poincaré group in the IR to something more fancy, like some Lifshitz scaling, hyperscaling, or you can break rotations, you can break translations. You can do that. And then holographically, we know how to do that. So you can get, for example, we did it already. I mean, it's already done in several papers. And the question is, what about the EFT? And indeed, okay, let me spoil what I'm going to say at Riken on Friday. If you consider the holographic superfluid in no-relativistic setup, you find out that there are situations in which the normal density at 0 temperature does not vanish. And this is a big puzzle for EFT, because the standard EFT description of a superfluid relies also only on Goldstone bosons at 0 temperature. So the question is, how can you write a field theory description of a superfluid, say Alanicolis or whatever you like, or like Son and friends, at 0 temperature, where you'd also have a normal density? And this is a result that, for example, came from holography. So yes, you can definitely do that. And indeed, I believe that holography is useful when you do that. So when you start, you know, breaking symmetries or playing with those things, because as you well known, you know, EFT and hydrodynamics are simple if the system is highly symmetric. If you start breaking symmetries, things become nasty. And apparently holography there, I think, can help. So the question, the answer is definitely yes, and it's more than yes. It's yes, and there are interesting things to think about it.
And you mean that you have can you implement a Galilean invariance for the holographic model?
Yeah. You can break boost. You can implement a different kind of boost, and you can have something like Galilean boost. Yes. It's more complicated, and of course, you know, it involves a bit of structure. You need the fields that basically break Poincaré invariant somehow, and but there are ways to study like superfluids or general fluids which are non-relativistic. Yes.
Okay. Thank you very much.
You're welcome.
Okay. Any other questions, comments? Maybe no. Okay. Let's thank the speaker again.
Thank you.
Thank you very much. So I will stop recording. Yeah, it's okay. Just a moment.